4.1, identifying linear functions. Okay, first of all, we have to go back to, we know what a function is. Not every set of ordered pairs, every relation is a function, right? Then we discover that some relations are not functions. Does anybody remember the definition? In your own words, doesn't have to be a technical definition. In your own words, what's the definition of being able to say a set of ordered pairs represents a function? Right?
1x for every y.
1x for every y?
Or 1y for every x.
Oh, exactly 1y for every x. It's the x that's in control, remember? It's the x that's in control, and every x value has to have only one y value. And if that's the case, we can say that that relation, that set of ordered pairs, is a function. So one of the first things we're going to do today is we're going to decide, first of all, if the relation, the set of ordered pairs, is a function or not. And then if it is, we're going to decide if it's a linear function or not. Okay? Because not every function is linear. So the first thing that we're going to fill in here says a function. They're already saying a function. We've already decided it is a function whose graph forms a straight line. We are then going to be able to call that a linear function. So we've already determined that it's a function. We see its graph. Its graph is a straight line. And if its graph is a straight line, we say it is a linear function. Okay, so it looks like you need your books open to page 238. So let's open your books to page 238.
Does not say 230.
Oh, sorry, 230, you're right. Thank you. Not 238, 230. And the directions for this, we're going to be doing the check it out problem 1A, 1B, and 1C at the bottom of the page. And the directions for it say, just what I've written there on your notes. Identify whether each graph represents a function and explain. So right now they're not even asking you if it's a linear function. They just want you to decide if it's a function or not. And we learned how to even tell from graphs whether they were functions or not. Then the second part of the direction says, if the graph does represent a function, is it linear? So if we decide it does represent a function, then we're going to take it one step further. So 1A, let's look at that graph. What do you think? Do you think that graph represents a function, or in other words, meets the definition Trey gave us that said, for each x value, there's only one y value? Isaac?
Yes.
Okay. So we're going to say, is a function, hold it anymore. Is a function each x value has only one y value? Is a function, our reasoning, each x value has only one y value. Do you remember how we can tell from a graph that each x value has only one y value?
If it's going like up and down, if it's on like 1.2 times.
Okay, if there's a point one above the other, right? If we have 2 points that are lined up vertically, 2 or more points lined up vertically, now that x value has more than one y value, doesn't it? Does that happen on this graph?
No.
No, it doesn't. Okay, well then they said, if the graph does represent a function, which we just said it does, is it linear? And what did we say up above? It's linear if what?
A function whose graph forms a straight line.
Okay, is that a straight line?
Yes.
Yeah, it's a straight line, so we're going to say, is a linear function. Is a linear function. Forms a straight line. They didn't say we had to explain that one, did they? So we get to do it like this. How do you feel about 1b? Take a look at it. First of all, the first question is it a function?
Yeah.
Represent
Yes.
a function. Okay, and our reasoning would be what? Trey, what's our reasoning for why 1b is a function? That's what we're going to say.
None of the points are on returns.
Okay, so each x value again only has
Yes.
one y value. You're going to feel like you've become like a repetitive machine because you're going to kind of oftentimes say the same thing. Is a function each x value, but we're going to get this so planted in our brain what a function means. Remember, some of us were having a hard time before saying it properly. Each x value has only one y value. Every time we write that, we're straightening out that confusing thought of how to say it's a function. Well, again, if it is a function, the question is it a linear function?
Yes. No, it's not. No, it could be. Yes, it is, because it's a straight line.
It's a straight line, isn't it? It's a straight line. It doesn't make any turns or anything, does it?
No.
Okay, so it is a linear function. Meets that standard also. Remember, every function does not have to be a linear function. Not every relation has to be a function. Not every function has to be linear.
So it can be like a curvy, or not like a not a function, but it can still be linear.
It can still be a straight line, but we wouldn't call it a linear function if it's not a function. So it can't become a member of the linear function family if it's not a function. It doesn't have the same last name, does it? It doesn't have the function part. Okay, let's look at 1c. How are you feeling about that one? First of all, is it a function?
No.
Okay, let's start raising your hands again. Is it a function? What do you think? Dakota?
Yes, it is a function.
It is a function? Okay, and what's your reasoning for it?
Each x value has only one y value.
Each x value has only one y value. Oh, looks like some people might want to challenge us on that, so let's just hold on for a second and see what the challenge is. And you got to be able to justify, you got to be able to convince Dakota that it's not a function if you don't think it is. Trey?
It's not because if you look at the curve, at the end of the curve, you see the two arrows over each other.
Well, the arrows are over each other. That's interesting. So in other words, it keeps going this way. Okay. Can we even be more specific? Can you give me an x value that does not have just one y value? Ariel? When x is equal to what?
2.
2. When x is equal to 2, there are two different places on that curve you can go to, aren't there? Yeah. So there would be 2 points lined up above and below each other. In other words, when x is equal to 2, there's a positive y value that goes with it, and there's a negative y value that goes with it, isn't there? So unfortunately, we are going to have to say, we're going to have to change Dakota's mind, we're going to have to say it is not a function. And there's only one place on that graph, only one place, and that's where it makes its turn, that the x value does not have. So let's state it like this. Most of the x values, there's only one x value on that curve actually that does not, where it turns. So we're going to say most of the x values have two different y values. And we have to use the word different. That's important. Most of the x values have two different y values. In fact, to even be more specific, they have a positive y value and they have a negative y value. Okay, my next question for you. So, are all straight lines a linear function? We get to just assume that as long as it's a straight line on a graph, that it's a linear function. What do you think? Dakota?
Straight line on the x value.
So Dakota says, what if you have a vertical line? Would a vertical line represent a function, first of all? It's straight, I'll give you that, but does each x value have only one y value? No, in fact, on a vertical line, there's only one x value, isn't there? All the x values are the same, but all the y values are different. So Dakota is right. We're going to have to answer that question no. And we're going to put some good notes in here. Why? No. A vertical line, in fact, it's the only one. It's the only one. A vertical line is not a function because its x value has several, and we could really use the word infinite, several different y values. The vertical line is not a function. It's the only straight line that is not a function. Because it has only one x value, and that x value has several different y values. So, a horizontal line, what did you say about a horizontal line? You had one. The horizontal line not a linear function?
Yes.
So the horizontal one is, when two terms becomes vertical, no, it's no longer a linear function. But anything else, horizontal and otherwise, other than vertical lines, represent linear functions. So any questions on these? So in your homework, when you do these types of problems, you're going to just use this as your guide. Tell whether it's a function, first of all, and then explain why or why not. And then if it is a function, decide if it's linear or not. Okay, let's go to the back then. See if you have anything that you have to see today. The other thing we're going to look at is if we have to determine if they give us a table of values, or in other words, they give us a set of ordered pairs instead of a graph. So we don't have the graph right now. We don't want to have to graph it to look at it. We just want to be able to tell from the table whether or not it represents a linear function. So here's how we're going to determine it. If we can find a constant change in x, the x's keep changing by the same amount. They keep going up by 1, or they keep going down by 2, or whatever. If the x's have a constant change, and then there's a constant change also in the y, they don't have to go up or down by the same thing the x's did, but they have to have a constant. So maybe the y's keep going up by 4s then. Or maybe the y's just go down by 1s. But as long as we have a pattern in both of them, we can say that we have a linear function. But that's adding and subtracting, just like our arithmetic sequences. Okay, so here's their table of values. They already put it in table form. How many ordered pairs are in that table?
4.
4. There's actually 4 of them. So let's look at the x's first. So as we go from this x to the next x, what happens to get from -2 to -1? It goes up by 1, doesn't it? How about to get from -1 to 0? Plus 1. So we were kind of checking to see if the x values form an arithmetic sequence right now, aren't we? How about from 0 to 1?
Plus 1.
It's going up by 1. So we found a constant change in x. Now let's see if there's a constant change in y. Does it have to be by going up by 1s? No, we just check to see if there's a constant change. So to go from 9 to 6,
Minus 3.
subtract 3. To go from 6 to 3,
Subtract 3.
subtract 3. Now don't stop, they're going to fool you sometimes. Don't quit until you've been through all of them. To get from 3 to 0,
Minus 3.
minus 3. So again, we're kind of looking for an arithmetic sequence in both x and in y. We have an arithmetic sequence going on. So what's happening here? As x goes up by 1, this is how we're going to show our work, write it out. Y goes
Down by 3.
down by 3. constant change in both of them. X's constant changes, it's going up by 1. Y's constant changes, it's going down by 3. So anybody got questions about that? So notice what my suggestion is going to be. What if they give it to you as a set of ordered pairs? My suggestion is write it in a table. It's easier to look at it and decide if we have, because remember we have to check for a constant change. I think that's what I want there. We want a constant change in X, and we want a constant change in Y. Or I guess what I wanted to do is to say change in X and change in Y, and then if they're constant, we know it's a linear function. So determine if a set of ordered pairs. In other words, they don't give it to us as a table. They just give it to us as a list of ordered pairs. So we're going to write it in a table with one extra step and do the same thing we just did. Check to see if there's a constant change in X and a constant change in Y. So when we put them in our table, we look at our ordered pairs, put the X and the corresponding Y side by side, right? How many ordered pairs do we have? 5.
5.
Okay, get your table filled out. Okay. What's going on in the X's? Let's see, -4 to -2, what happens? Add 2. Okay, you guys figure out the rest of them on your own. Figure out the rest of those changes in X. What happens as you go down the X column only? Don't worry about the Y's right now. Do they keep going up by 2s?
Yes.
Yes, we have a constant change in X. Can we stop?
No.
What else do we need?
The lines.
We need a constant change in Y now. We gotta check to see if we have that. So from 13 to 1, what do we get, Seth? Okay, is it going up or by 12 or going down? Down. So if it's going down, we needed to make it a -12, right? Malcolm, what's the next change? Do you know? From 1 above 0 down to 3 below 0. What did it do? It dropped 4, didn't it? So it goes down 4. Do we need to keep going on even? No, actually we don't, but we'll just check it out and see what happens. To get from -3 to +1.
+4.
+4. Now it's changing direction and going the other way. Or I guess it had already changed direction. It's going up every time. But is it going up by the same amount? No, it's not. It's got now it went up 12. So is that a constant change in Y? Okay. So is this a linear function then?
No.
This is not a linear function. So we would say not a linear function and our reasoning, the Y values do not have a constant change. And again, yes, you have to write these things out, because that's what helps us remember the reason yes, or the reason no. Why is that argument? So we'll start changing this. Okay? You're going to feel like lots of times you're writing the same thing, but that's okay. So here it was not a linear function, our reason. And it doesn't have to be the y's that don't have a constant change. Maybe it's the x's that don't have a constant and while the Ys did instead. It can be vice versa. Or if it does have a constant change, we describe that constant change. What's actually happening? In this first one we did, as x goes up by 1, we said y goes down by 3. So question.